Ever heard of numbers that can describe, like the chaos of shuffling a deck of cards?
Or maybe how about those that can help you understand like the ups and downs of the stock market?
Well, get this. You actually submitted some excerpts from Wikipedia all about Stirling numbers, and that's what we're diving into today.
They're really fascinating, like a hidden language that can unlock all sorts of patterns in things like permutations and partitions.
Permutations and partitions, huh? Sounds kind of complex.
It might sound a bit intimidating at first, but trust me, by the end of this deep dive, you'll have a whole new way of thinking about things like ordering and grouping and, predicting patterns.
Okay, I'm ready to unlock these
All
patterns.
right, let's do it.
So, where do we even begin with something like this?
Well, a good place to start is with something called Stirling numbers of the first kind.
Stirling numbers of the first kind. Okay, so what are those all about?
Well, let's start with a simple example.
Yeah.
Imagine you're setting up chairs for a dinner party. Let's say you have 5 chairs.
Okay, 5 chairs, got it.
How many different ways could you arrange your guests in those chairs?
Hmm. Well, that would be 5 times, 4 times, 3 times, 2 times 1, which I believe is 120.
Exactly. 120. In mathematicians, they call this a factorial.
Okay, 5 factorial is 120. I remember that from math class. But what does that have to do with these Stirling numbers?
All right, well, now imagine instead of having all the chairs lined up in a row, you arrange them in a circle.
Oh, in a circle. Okay.
So now some arrangements that were different before are actually considered the same because, you could just rotate the circle.
Oh, that's true. Like if everyone shifts one seat to the left, it's still the same basic arrangement.
Exactly. And that's where the idea of a falling factorial comes in.
A falling factorial. Okay, that sounds kind of ominous.
It's not as scary as it sounds.
Mm.
It basically helps us account for these circular arrangements where, some arrangements are equivalent.
So the falling factorial is like a factorial, but it takes into account that some arrangements are the same in a circular setting.
You got it. And when you express this falling factorial as a polynomial, Stirling numbers of the first kind appear as the coefficients. They're like these little signposts that tell you how many different circular arrangements you can have.
So in our example with 5 chairs, these Stirling numbers are telling me how many different ways I could arrange my guests around a circular table.
They can tell you even more than that. Think about shuffling a deck of cards. Each shuffle is a permutation. That's just a fancy word for a specific arrangement of the cards.
Right, like every time you shuffle the deck, it's in a new order.
Exactly. Now, a cycle happens when, say, the top card moves to the bottom card moves to the middle, and the middle card moves to the top. So they've just cycled positions. Stirling numbers of the first kind count how many permutations have a specific number of these cycles.
Wait, so these numbers can help predict how many shuffles it takes to return a deck of cards back to its original order.
That's exactly right. And it gets even more interesting. We actually have 2 versions of these Stirling numbers, signed and unsigned.
Signed and unsigned, what's the difference?
Well, the signed ones can be either positive or negative, while the unsigned ones are always positive. And it's specifically the unsigned ones that count those permutations.
Okay, so the signed ones have something to do with positive or negative values, but if we want to just count the permutations, we use the unsigned ones.
Precisely.
Got it. So is there like an easy way to calculate these Stirling numbers? Do we have to go through all those falling factorials and permutations every time?
Well, there's actually a really cool shortcut called a recurrence relation.
Recurrence relation, what's that?
It basically means you can calculate a Stirling number by using the ones that came before it. So you don't have to start from scratch each time.
That definitely sounds easier. Are there any other ways to like visualize or work with these numbers?
Absolutely. You know Pascal's triangle, right?
Oh yeah, that triangle where each number is the sum of the 2 numbers above it.
That's the one. Well, Stirling numbers have their own version of a triangle, which can reveal all sorts of fascinating patterns, too.
So we have patterns and formulas and even a triangle for these Stirling numbers of the first kind. Pretty impressive.
It is pretty cool, right?
It is. But you mentioned that there's a second kind of Stirling number. How do those fit into all of this?
Ah, yes. Stirling numbers of the second kind. Well, while the first kind is all about permutations and cycles, these ones shift our focus to grouping, specifically something called partitioning.
Partitioning, does that just mean dividing things up into groups?
Exactly.
Okay, I think I'm starting to get the hang of these Stirling numbers of the first kind, but you mentioned there's a second kind too.
Right. Stirling numbers of the second kind.
How do those fit in?
Well, the first kind is all about permutations and cycles, right?
Right.
Stirling numbers of the second kind are all about grouping,
Mhm.
specifically something called partitioning.
Partitioning.
Yes.
Does that just mean, like, dividing things up into groups?
Exactly.
Yeah.
Like, let's say you have a bag of marbles and you want to divide them into smaller bags.
Right.
That's partitioning. And Stirling numbers of the second kind tell you how many different ways you can do that.
Okay, so instead of arranging guests in shares or shuffling cards, now we're putting marbles into bags.
You got it.
Yeah.
It's like deciding how to form teams for a project.
Okay.
Imagine you have 4 people.
Hmm.
How many different team combinations could you create?
Well, you could have everyone working individually.
Right.
You could pair them up.
Yep.
You could have a group of 3 and one person by themselves.
Well,
Or everyone could work together as one big team.
exactly. And each of those different team combinations would be a different way to partition the group of 4 people.
Oh, I see. And the Stirling number of the second kind for that scenario would be 5, since there are 5 different ways to make teams.
That's exactly right. Stirling numbers of the second kind help us count all those different possibilities.
This is starting to make sense.
Good.
So are there any helpful formulas or patterns for calculating these Stirling numbers of the second kind, just like with the first kind?
Absolutely. There's a recurrence relation for the second kind, too,
Right.
which means you can calculate them step by step using the previous numbers.
Okay.
And here's where things get really interesting. Remember how we talked about the inverse relationship between multiplication and division?
Yeah, like multiplying by 2 is the opposite of dividing by 2.
Exactly. Well, there's a similar kind of inverse relationship between Stirling numbers of the first and second kind.
Oh, really?
Yeah, you can visualize this relationship using something called matrices.
Matrices.
Yeah, they're like these grids of numbers arranged in rows and columns.
Oh, yeah. I vaguely remember those from high school math.
Well, think of it this way. The Stirling numbers of the first and second kind can be arranged in matrices.
Okay.
And when you multiply these matrices together, you get something called the identity matrix.
And what's the identity matrix?
It's basically like the number one in multiplication. It doesn't change anything.
Yep.
So the fact that these matrices multiply to give you the identity matrix shows that the Stirling numbers of the first and second kind have this special inverse relationship.
Wow. That's a pretty cool connection. It seems like these different types of Stirling numbers are more intertwined than I initially thought.
They are.
And speaking of connections, you mentioned there's even a third kind of Stirling number.
Right?
The law numbers?
The law numbers.
Where do they fit into all of this?
Yes, the law numbers. They add another layer to our understanding of arrangements.
Okay.
Remember how we talked about falling factorials when discussing Stirling numbers of the first kind?
Yeah, where we started with a number and kept multiplying by smaller and smaller numbers.
Exactly. Well, law numbers come into play when we express those falling factorials using something called rising factorials.
Rising factorials. So instead of subtracting, we're adding each time.
Precisely. With rising factorials, each number is one more than the one before it.
Okay.
And law numbers are the coefficients that pop up when we rewrite those falling factorials in terms of rising factorials.
Okay, I think I'm following so far, but how does this relate back to the idea of arrangements or groupings?
Well, law numbers are all about ordered partitions.
Ordered partitions.
Yeah, so instead of just dividing objects into groups, now we care about the order within those groups.
Okay.
So think back to our team example. Not only are we interested in the different team compositions, but now we also care about things like who's the leader of each team or the order they present their work in.
Oh, so it's like we're adding a layer of hierarchy or structure to those groups, and law numbers quantify the different ways to do that.
Exactly. It's like taking our understanding of arrangements to the next level.
Wow. These Stirling numbers are really a rabbit hole of mathematical connections. We've got these 3 types, the first kind dealing with cycles, the second kind focused on partitioning, and now these law numbers that bring in ordered partitions.
It's pretty amazing, right?
It is. But I'm curious, why should we even care about these numbers in the first place?
That's a good question.
What can we actually do with this knowledge?
That's the best part. Stirling numbers have this remarkable ability to pop up in all sorts of unexpected places, connecting seemingly unrelated fields like computer science and statistics and even physics.
Really? But how can something so abstract have real-world application?
Oh, absolutely. Let's take computer science, for instance.
Okay.
Stirling numbers of the second kind are incredibly helpful in analyzing certain types of sorting algorithms.
Sorting algorithms, you mean like the methods computers use to organize data?
Exactly. Think about how a computer might sort a list of numbers from smallest to largest.
Okay.
There are many different algorithms for doing this, and some are more efficient than others.
Right.
Stirling numbers of the second kind can help analyze the efficiency of these algorithms by quantifying the different ways data can be partitioned during the sorting process.
So by understanding these seemingly abstract Stirling numbers, computer scientists can design faster and more efficient sorting algorithms. That's pretty amazing. Are there any other applications you find particularly fascinating? That connection to sorting algorithms is mind-blowing. It seems like these Stirling numbers are like this secret code that unlocks hidden patterns in all sorts of unexpected places.
They really are. And what's fascinating to me is how these simple combinatorial ideas about arranging and grouping, they can actually lead you to some of the most profound concepts in mathematics.
Oh, really? Like what?
Well, did you know that Stirling numbers have connections to things like Riemann zeta functions and pi, and even the gamma function?
Oh, hold on. Riemann zeta functions. Those are some pretty heavy-duty mathematical objects.
I remember hearing about those in a documentary about prime numbers.
Yeah?
What in the world do they have to do with Stirling numbers?
It's a bit like discovering a secret tunnel that connects two completely separate parts of a city.
Okay.
Riemann zeta functions are these incredible tools that help us understand the distribution of prime numbers, and they have these deep connections to complex analysis and number theory.
And it turns out that certain formulas involving Stirling numbers can be used to express these Riemann zeta functions.
Wow, so we're talking about a connection between the very basic idea of arranging objects and some of the most fundamental questions about prime numbers.
Exactly.
That's incredible.
It really highlights how interconnected mathematics is. Even something as seemingly simple as counting arrangements can have these profound implications in other areas of math.
You mentioned the gamma function, too. What's that all about?
The gamma function is kind of like a generalization of the factorial.
Okay.
Remember how we talked about factorials earlier, like 5 factorial being 5 times 4 times 3 times 2 times 1?
Right.
Well, the gamma function extends that idea to include not just whole numbers, but also fractions and even complex numbers.
So instead of just calculating 5 factorial, I could calculate, say, 3.5 factorial using this gamma function.
Exactly. And it turns out that Stirling's formula, which involves Stirling numbers, gives us a really accurate approximation for the gamma function when we're dealing with large numbers.
This deep dive has definitely opened my eyes to a whole new world of mathematical beauty and complexity. I have a feeling I'll be seeing Stirling numbers everywhere now.
I wouldn't be surprised. And here's something to ponder as you go about your day. How do Stirling numbers relate to the idea of entropy?
Entropy, like the measure of disorder in a system.
Exactly.
I remember learning about that in physics class.
Think about how Stirling numbers quantify the different ways to arrange and partition things.
Okay.
In a way, they're also measuring the potential for disorder or complexity.
So could they offer like a new way to think about the increasing complexity of information in our digital age? With so much data being generated and shared every second, it seems like entropy is just constantly increasing.
That's a great observation. Perhaps Stirling numbers could help us quantify and understand that growing complexity in new and insightful ways.
That's a fascinating thought to leave our listeners with.
It is. And I challenge you all to take a look at your own world, your work, your hobbies, even your daily routines, and see if you can find a way that Stirling numbers might offer a fresh perspective on the patterns you see. You never know what hidden connections you might uncover. That's all the time we have for today's deep dive into the fascinating world of Stirling numbers. Until next time, keep exploring, keep questioning, and keep diving deep.